All right, welcome to Anatomy, and we'll be doing some notes today on some basic chemistry. We've done some of the elements of the body we've talked about, and we're going to do atoms and bonding. That's going to set you up for biochemistry and all the organic chemistry molecules that we need to know for the cell and for function in your body and for the physiology part. What we're reviewing is what's matter, right? What's the matter? Well, everything, right? Everything is matter. Anything that has, though, specifically takes up space and has mass is what we're calling matter. All right. And we talked about the elements of the body, there being the building blocks of matter, elements of the building blocks of matter. And what are they? Well, they're different types of atoms. Okay, so we're going to be talking more specifically about atoms, but elements are the different types of atoms that are out there. There are 92 naturally occurring elements, so elements in nature on this planet. There's actually 118 on the periodic table, but most of those happen like in a laboratory or very quickly appear and then disappear. Compounds that could be formed in the body. They have elements in them that are bonded together. We're going to talk about those bonds also today, like water, CO2, or glucose, which is C6H12O2. So the formula tells you how much of each element is in that compound. So water has different properties than just hydrogen alone and oxygen alone, but when you link them together, they form water, and everything in your body depends on water. Carbon is its own element, found in coal and in your pencils, made out of carbon, graphite, and oxygen, what you breathe, you put it together, and it's CO2. It's a byproduct. And you don't want too much CO2 in your body because it displaces oxygen. And of course, glucose, 6 carbons, 12 hydrogens, and 6 oxygens. That's what that number means when it's to the right and bottom of that capital letter. So the capital letter is the element symbol. And we've already talked about these being oxygen is 65% by mass of your body. Carbon is 18.5% by mass of your body weight. Okay, this is of your body entirely. Hydrogen is the third most common as far as the most in the weight of your body. It's 9.5%, but actually hydrogen is more prevalent because there's more hydrogen attached to all your molecules than any other atom. They just don't weigh very much. They just weigh one. Nitrogen is also one of the big five, and it's at 3.2% as the percentage weight. And then calcium's at 1.5. That's the abbreviation of calcium is Ca, capital C, and then there needs to be a second letter to distinguish the calcium from the carbon, so we have to put that lowercase a there, and that's at 1.5%. Phosphorus at 1.0, and then we get potassium and sulfur and sodium and chlorine, and they're all less than 1% in your body. So we've already had a discussion about that, and we're going to move on. You do need magnesium, and you do need iodine in your system, and iron, and you need all these trace elements like fluoride, and that's the abbreviation fluoride is F. Iron has to be capital F for like ferrous, because to distinguish it from iodine, so it couldn't be an I, and to distinguish it from fluorine, it had to be capital F, lowercase e. Okay, those are all less than 1%. You also have things like chromium to help with your blood sugar regulation, and cobalt, copper, lithium, manganese, molybdenum, selenium, silicon, tin, vanadium, zinc. Goodness gracious, lithium. Did we ever say lithium? You need a lot of different trace elements, even a little tiny of arsenic. This is in a lot of cases, it's part of your structure, but it's also the enzyme function. Is what most of those are involved in. So, hormone production, hormones, structure, and refer to my notes for some more information on that. So we're back to atoms, just talking about atoms themselves and their structure. All right, so to define what an atom is as opposed to other types of matter is we're going to say atoms are the smallest unit of matter that retain its properties that are unique Atoms are made of other types of matter. We call those subatomic particles, but they don't have their own individual, distinct, unique properties. Atoms do, because they're different combinations of your protons, neutrons, and electrons. Here, let me write that in some different colored pen because I like to. All right, protons, you can see in our picture here, they're in the nucleus, and maybe you can see they're attached to a positive charge. Protons are positive, so we give it a little plus sign, and they weigh approximately 1. So they have a charge of positive 1, and we give it a weight of 1. We just decided 1 proton weighs 1 atomic mass unit. All right, we made that up, but that's how that goes in science. You're like, cool, I'm going to make that a weight of 1. Everything else is compared to protons. Neutrons are kind of similar in weight, but they don't have any charge. They're neutral. Also in the nucleus, neutrons in the nucleus, that's cool. They kind of stabilize the protons in the nucleus. And its charge is 0. Its weight is 1 as well. Electrons, that's where it gets weird because they are tiny, and even though they have a nice negative charge that is equal and opposite to protons, they basically are almost 1/2000th of the mass of a proton. So we don't really consider their weight, just their charge. And they don't weigh much. They fly around the nucleus. They don't fly in distinct exact orbitals like this picture. There's more of like a cloud, electron cloud. Give it a weight of 0. And how many electrons you have is going to depend on the protons or what the shells are. There's a pattern, though, okay? So that's what's going to give the atom a unique identity is how many protons it has, okay? And then neutrons are going to affect the mass and maybe the stability, atomic mass units. And electrons are going to affect the charge. So the identity of the atom, it's really important that we kind of put down what's here. The protons and the neutrons are in the nucleus. So I'm going to say, NU, and there we go. They're in the nucleus. Okay. And it's a dense cloud. So that's where the protons and neutrons, and that's where the mass is of the atom, basically. Electrons don't really contribute to the mass. The electrons are flying around in a cloud. Why don't we put here, too, that protons are the identity. If you have 6 protons, you have carbon. If you have 3 protons, you have lithium. Okay? If you have 8 protons, you have oxygen. All right, so protons are the identity of the atom. That's important to note. The mass might be the protons plus the neutrons, but not the identity. And then electrons, of course, they can be used to neutralize the protons, but they're flying around in what we call an electron cloud. That's not really demonstrated very well here. You probably would just be flying around, and it could be spherical in shape. The first orbital could be spherical. Then it could look like a baseball bat or donuts, or there's different kinds of electron clouds depending on the energy level of that the electron is in. All right, so maybe you make that a cloud. That's where the electrons live, right? But they are in distinct levels depending on their energy and depending on how many of them are there and present. So they can be gained or lost, and they're going to change the charge, which we'll talk about a little bit later. Isotopes are the same element, like maybe you have an isotope of oxygen, but it's going to have a different number of neutrons than what's normal, okay? I'm going to say pound sign means also number of neutrons. All right? So they're going to have a slightly different atomic weight. We call that atomic weight or atomic mass. And that's why the periodic table shows you some weights, but it doesn't give you a whole number for atomic uh, mass. All right, it's going to be an average. It's going to be a decimal. This is my little periodic table. And for example, mercury, we say 200.59, and you're like, there's a 0.59 of a neutron. Can't have a point. Now it's an average, is because some of them have more neutrons or less. So we round it when we're using the atomic mass for calculations, because we can't have half a neutron or half a proton. All right. So isotopes, they might be a little bit heavier, therefore a little bit less stable, and that might give you some radiation. So isotopes that are unstable and emitting radiation are called radioisotopes. They have an unstable nucleus, and they're going to emit all kinds of radiation. The nuclei basically are breaking apart. Another word for that is decompose. That's why it's releasing energy. It's because as it's breaking apart. So some radiation it can release are alpha. There's a little Greek letter for alpha. Remember, he is the laughing fish. Okay? He's got bubbles. He's having fun. Bubbles. He's playing around with helium. So, yeah, he's laughing. He. Yeah. Alpha is radiation is just a helium particle, and you're like, helium? I didn't think helium was dangerous. Well, yeah, it's not unless it's flying out at you at a billion miles per hour. It doesn't last very long. It's not a very long distance, but it is some pretty powerful radiation. That's the way that scientists like to write it. They like to write the mass at the top and then atomic number at the bottom, and the atomic number is 2 for helium on the periodic table. If you have 2 protons, you have helium. Usually it has 2 neutrons, and you can tell because you take 4 minus 2, and helium has 2 neutrons. Remember, the mass is also the number of protons plus neutrons. It's all having to do with what's in the nucleus. Remember, we gave neutrons a mass of 1 and protons a mass of 1. So we count them. They're counted here. And in total, helium has a total of 4 protons plus neutrons. That's its atomic mass. So that's how you calculate the number of neutrons. Another radiation that you can have that's pretty common is beta. There's that beta. I always think of beta as bad, but it's not really. It's just a little negative. So beta is an electron. And you know how we relate the number of protons at the number at the bottom? Well, it's an electron, so it's really just an electron flying around. But we give it a nice abbreviation of E, just to round that out. And then nuclear chemists like to put it as a -1 at the bottom, because it's like equal and opposite to the protons. Get it? And then it has a mass of 0. So when you do calculations in radiochemistry or nuclear chemistry, that's how you represent it, and it works out and makes the calculations work. I'm not going to require you to know this for this class, but just remember there's alpha radiation, beta radiation. Of course, electrons flying at you at a very high speed is going to be dangerous, and it can go farther than alpha radiation. Also, yeah, we might want to talk about gamma. All right, gamma radiation, yeah, like Incredible Hulk, is just kind of units of energy that are given off as a byproduct of other radiation. So we don't give it an identity exactly, because it's more just waves of energy and not a particle that we can kind of define in what we already know. So yeah, these are the 3 types of radiation, alpha, beta, and gamma, that we usually study. There's other types, honestly. You could have a positron. I know, sounds scientific. Sounds really sounds sci-fi, but it's true. Positrons exist. So it's 1 proton, therefore it's a hydrogen, and it only weighs 1, because hydrogen's atomic mass is 1, because it doesn't have any neutrons. It doesn't technically need them to be stable. It could, an isotope of hydrogen could. But these are just regular hydrogen as radiation, so flying at you at an incredible rate of speed because of the energy being given off. You could have a neutron, atomic mass of 1 and a charge of 1, basically, I guess. And neutron radiation. Yeah, I know. I said it. Yeah. So these subparticles can become radiation when flying out at you, I guess. But not usually a proton, neutron, electron, that can all be radiation. And then helium. Why not, right? It's next to hydrogen on the periodic table. Might as well. Chemical bonds, we're going to talk about next. Most elements actually exist as combinations of atoms. They're not usually just the element itself. Therefore, atoms must be bonded together. There's different types of ways to bond atoms, just like there's different types of ways of holding pieces of paper together. All right, some better than others, depending on the function. Maybe some stronger than others. You could staple paper together, glue it, or tape it. But there's some basic rules for bonding. Bond formation involves an interaction between electrons, most importantly, between valence electrons. Valence are the outer electrons, and so they're more accessible. They're on the outside. There's other energy levels that are filled with the electrons there, but the outer shell is what's going to interact with other atoms and maybe bond together. All in this together. So outer electrons, valence electrons. Electrons, they orbit the nucleus in shells or orbitals. It's just kind of a misnomer because they're not orbiting in a circular pattern. They're flying around in a certain type of shape, I guess, in certain space. The first innermost energy level contains a maximum of 2 electrons. This energy level will fill first. Okay. And the periodic table is designed to reflect that because it affects the chemistry and bonding. Second energy level is stable when it contains a maximum of 8 electrons. And then we're going to say that the third level also stable when it contains 8 as well. Now, there's some hanky business with the extra large atoms or larger atoms because they start to put electrons in a weird drop D orbital, I like to call it. But we're not going to study that in this class. We're going to talk about 2, 8, and 8, the rule of 8. Okay? 8 electrons, atoms wanting to reach a stable configuration, they're pretty much always wanting to get 8 electrons to be stable, right? In a full orbital. Okay. Most atoms are trying to do this, except for the noble gases. They have a full orbital already on the outside, and they're stable. But most of them are not naturally stable, and they tend to gain electrons to be stable, lose electrons to be stable, or they could also be kind and share electrons in order to fill their outermost shell. Most atoms are going to form these bonds with other atoms in order to reach that configuration. Okay, so that's why bonding happens. The nice part is the periodic table is also, if you're into chemistry and you're a nerd like me, it's arranged to show you that here's my notes on here that the rows are actually representative of the electron orbitals. So the first row is like the first orbital. There's 2 elements in that first row, and then that orbital will be full, and then the second and third row have 8, 2 here and 6 here. And for the fourth row, we kind of have to skip the transition elements because this weird drop D orbital, they could give or lose, or they always lose because they're cations, but they could be happy with one situation or another. So they transition. We just skip that and just realize that the next 6 is the fourth orbital, I guess, in this class is what we call it. So we're going to show you a little bit of what the ionic bond looks like in a second. But first, we got to tell you what an ion is. An ion is any atom that has gained or lost electrons, or even just 1 electron. Yeah, that stands for electron. Okay, so let's look at some atoms and the orbitals and see why they might want to gain or lose real quick. All right, so right here we have sodium and chlorine. And as you could see, maybe we haven't said it or not, sodium, it's going to have 11 protons. So it's 11 positive charges. So a neutral sodium atom has to have 11 electrons. To start out with, it does. It's not stable, but that would be what a neutral sodium atom would have. 2 in the first, like we talked about, 8 in the second. We always spread them out north, south, east, west, and pair them because You can easily see if it's full or not. It looks full, 2 pairs in all directions. And then so that's 10 so far, but the 11th is in that outer shell. It's not a full shell. Sodium is not happy. Right now, he's not happy. Okay. Chlorine is going to have 17 electrons because there's 17 protons, at least initially. So 2 in the first, 8 in the second, and then the last 7 in that outer shell. So you can see chlorine is super willing to probably just gain an electron, just needs one more, and it'll have a full shell. And sodium is super willing to donate an electron to get rid of that shell that's not full. So that's what indeed happens. And then they become happy because they are stable. All right. So it becomes, I'll write that down there here. Let's see, a charged particle. So if they're going to become charged particles. Here, that's what goes here. You have a sodium ion and a chlorine ion. So the sodium has lost an electron. It has 10 electrons and only still, of course, 11 protons. Otherwise, it wouldn't be sodium. And so it becomes a +1 charge. The chlorine still has its 17 protons, but now has 18 electrons. So the electrons outweigh the protons by 1. So its charge is +1. Chemists are lazy. We just put the plus sign once and on the negative sign once to show that. So these are 2 ions, and they stay together, though. They still stay together. Why do they stay together? Because they're mildly attracted, because, opposites attract. And that's what we call an ionic bond. We created like 2 parts of magnet, a positive ion and negative ion. And that's kind of why they stay together. They're not a very strong bond if you put water with them. They dissociate and hang out around the other parts of the water molecules instead of each other in water. But when they're not in water, they're pretty solid, strong, but brittle compounds. All right, so there it is. Remember, ionic bond is relatively strong in its solid state, but it gets weakened. We're going to call it polar solutions. Okay, have to distinguish that because they have to be polar solutions that are going to be able to attract the cation, the positive ion, and attract the negative ion and take them apart. By the way, yes, these are kitty cat ions if they're positively charged, and they're anions if they're negatively charged. And I think the kitty cat, if you want to remember kitty cat ion, its plus sign could also just be on its side, whiskers, and it could be a kitty cat. And I guess anions have a little negative sign in them. I don't know. They're a little negative. Like the antagonist in the story could be could be negative. All right. It's important for the story. All right. So this forms table salt, by the way. Here's the formula. 1 sodium and 1 chlorine like to hang out around each other. And then they dissociate. Here's the equation in water. So put AQ now that we added water. And they don't just dissolve. They mix well with water, but they also break apart. We call that dissociation. So water is a polar solution, which we'll talk about soon. And that's why bound ions may separate into their free positive and negative ions. But this is important. It's called dissociation. Yeah. There, period. Nothing goes there. This is important because many of these ions are needed in chemical reactions in the body. For example, the cell lining of the stomach. They need to be able to produce hydrochloric acid. That's 1 hydrogen ion and a chlorine ion or chloride ion. You put an IDE ending on an anion that is negatively charged when it's a single element anion. And so it needs the chlorine from the table salt in order to make this necessary chemical in your body. So it's important that salts dissolve and dissociate and become available for moving. Also, your muscles, they polarize and depolarize by the movement of ions across membranes in the watery solution of your body, in and out of the cells. And that's how it's the muscles able to polarize and depolarize, and nerves too, so that they can function, which we'll talk about later. So we're going to talk about another type of bond, the covalent bond. You think of covalent, it's you think of coworkers and you share office space in your company. You're all in this together. They like to share electrons. Okay, so covalent bond is when electrons are shared. So they're kind of the hippie um, of the atoms, I guess. They don't become ions, but they are able to reach a stable configuration because they feel like they have more. All right, these are stronger bonds. Remember how the ions are only held together by a positive negative attraction and be like, hey, you look cute, you're oppositely charged, let's hang out. It's not that strong of a relationship. This is a better relationship for you because, they share a lot. All right, so let's do carbon. And for carbon, I'm just going to put a C, and then I'm going to put its electrons. Remember, it has 6, so 2 in the first, and then its outer shell has the rest, and then would only put 4 in here. It's important to note carbon is great. We're going to talk about carbon because it has 4 different electrons, and it can share those 4, and then whatever atom it's sharing its 4 with, maybe one at a time, whatever atom it's sharing electrons with, that atom could share with them in 4 different locations. Okay, so in this case, maybe it's not the best example here. Oxygen has 8 electrons, 2 in the first, 6 in the second. I'm going to draw it just a little bit weirdly here. Nah, it's all right. Sorry. Forgot to shut that door. And I'm going to actually have a bond form between these 2 electrons. This one's going to share that one, and carbon's going to share his. So carbon shares his electron, oxygen shares carbon's electron, and then, they both get to feel like they have more. All right, but this is great because oxygen, in this case, it could share 1 electron, but it really wants 2. So it actually shares its other electron with carbon, and carbon shares its other electron as well. So actually 2 bonds formed between this carbon and this oxygen. And if you have oxygen present in this reaction, you may need to have carbon bond with another atom of oxygen. Remember, 8, 2 electrons in the first, 6 in the second, and I'll do it that way so that this oxygen can also share its electron with carbon, and carbon can share its electron with oxygen. But also up here, carbon needs 1 more, and so does oxygen. So we actually, in this case, kind of rare, you have double bonds between the carbon and oxygen. Oxygen can form double bonds, but carbon, the main thing is to realize carbon makes 1, 2, 3, 4 bonds. It needs 4 electrons, so it can make 4 bonds with usually 2 or more other elements. So that's important because these are strong bonds, and one atom has 4 electrons to share with others, and it's going to form covalent bonds, maybe with other carbons, with hydrogens, with oxygens, with nitrogen, and other elements. And those are the ones that are like close to being full, and they could just share. They don't want to lose electrons. It may be not obvious to you, but when you're finding valence electrons, you count from the left because the shells are full at the end of the row. And say boron has 2 electrons in the first, and then its last 1, 2, 3 electrons in the outer shell. And so that's how you can tell what this electron configuration is going to look at without having to make this Bohr diagram with all the electrons in it. You can find out the outer electrons by finding the atom here on the periodic table and counting 1, 2, 3, 4 electrons in carbon's outer shell. Yes, it's very important. Okay, to count from the left to find the valence electrons. Okay, so carbon does this, and it could do it in 4 different directions. So it's a really nice building block. It's like a fancy Lego, and that's how we can build all life on Earth. Carbon is the building block of all life and all the organic molecules that make us living beings. You can't have a living being on Earth without carbon. So all organic compounds are complex, precise arrangements of these non-metal. I'm going to say non-metal. All right. So giving out the periodic table again here, like little rainbow periodic table, metals could be the alkaline metal, could be alkaline earth or the transition metals or other metals or metal-ish things. But non-metals are in what I like to call covalent corner. They're very close to having a full shell because at the end of the row, they're really close to looking like this noble gas over here. Remember, noble gases are non-reactive, so they don't really involve themselves with covalent corner. But these guys are the ones that are wanting to share electrons because they're like, hey, if you don't have any to give to me, why don't we just share with each other? Okay, so it's a lovely little arrangement here. Carbon has those bonds, and it's going to want to form bonds with other non-metal atoms. I'll just write right over there. And we're going to be covalently bonded. All right. All right, remember to find valence shells, valence electrons, you count from the left. Yes, count. Use the count. Yes, he loves it when you use the count. All right, count from the left. To find valence electrons. Sorry, I abbreviated that too much. Here we go. All right. Count that element as well, but that's just all that we are worried about. Covalent bonds, that because electrons are shared, they're relatively strong and are not weakened in water, which is good. You don't want to jump into a swimming pool and then disassociate and all your atoms pull apart, right? It's good. Maybe the Wicked Witch of the West does not have covalent bonds. She must be all ionic bonds because she dissolved in water, supposedly, unless you saw Wicked, and then you knew that wasn't the real story. But that's okay. This is important, though, to have strong covalent bonds. Okay. For example, your membranes that make a cell, and separate the contents of a cell and give a cell structure. It's got to remain intact if we're going to function properly in our watery environment that we need, that's both inside and outside our cells. We're mostly water. All of our chemical reactions happen in water, folks. All right. So we're going to talk about a certain type of covalent bond. It's important. It's called a disulfide bond. They are from sulfur, and they're only in protein. We're going to talk about proteins later. But it's an important covalent bond formed between two atoms of sulfur, usually within the same large protein molecule. Okay, it's going to give shape. It's going to allow the shape to be permanent because it's going to be locked in with that covalent bond. Proteins have covalent bonds too, but they only have them laterally or in a line, and this will help make three-dimensional structure, which we'll talk about. Many proteins have that 3D structure specifically so they can function or structurally provide a certain support. And these disulfide bonds are going to help maintain that shape and function. Example proteins that depend on disulfide bonds to maintain their shape are keratin. That's like your calluses and like hair and skin. And, I was supposed to put that down there, but that's okay. Here, let me put keratin. Insulin, a hormone that you need for getting sugars into your cells, or they can't get the sugar in the cells to even do cellular respiration and make energy. So you're going to need insulin. That's another one that has a lot of the sulfur bonds. And then maybe like thyroid stimulating hormone, also follicle stimulating hormone. Just saying that there are a lot of important molecules in your body that rely on disulfide bonds. And if you want to see a disulfide bond, for example, sulfur has 8 electrons in its outer shell. It's very similar to oxygen. We're just going to do the Lewis dot, by the way. Instead of including all the shells with electrons that are inside and don't involve themselves with bonding, I'm just going to put the outer electrons. Sulfur, counting from the left, you're going to see it has 6 electrons. So go ahead, put those 6 in here. I'm going to assume the sulfur is bonded to the rest of the protein. So just go like that. And then it wants and so there's its 5th, and here's its 6th electron. So it's sharing an electron with the amino acids attached to. So I'll just put AA for amino acid. There you go. Then there's another sulfur on the end of an amino acid, which we will talk about. All right. And then the sulfur shares its electron with the other sulfur and vice versa. And it's a covalent sharing bond, and it's very tough. It's a good, strong bond. All right. So that's disulfide bonds. Those are covalent bonds. Now you can have covalent bonds that aren't equally sharing electrons. Okay. It's kind of like shared custody. Maybe you spend more time at one parent's house than the other. I don't know. Not everything in life is totally fair. So we call it a polar molecule because it's polarized. One side has electrons more often than the other. So it kind of gives it a slight negative charge. All right. So we're just going to give it a uneven electron sharing. And it has to do with like the number of protons in the nucleus of the atom, and also the size of the atom and how far away these electrons are. Electronegativity is something you can look up and study that. But the entire molecule then is going to, if it's polar and it shares one side with less electrons, it's going to be a little positive. I like to put in parentheses because it's a partial positive. It's not a +1. It's not a total positive. It's just a little less negative since the electron is spending more time on the other side, which makes that side partially negative. So it can be attracted then to other polar molecules or ionic molecules because they also, if they have a plus side and a positive end slightly and a negative end slightly, or if they have a positive cation and a negative cation, they're going to really gel with each other. And this is why they dissolve very well in each other, because they're attracted, and they're attracted to other polar molecules. You know, how like dissolves like. So polar molecules and ionic compounds, like salts, they dissolve really well in water because water is polar. And I'll show you. I think it's on the next page. It's on page 4 in our notes. We did pages 2 and 3 already. Here's Mickey Mouse. Just kidding. This is water. This is hydrogen. It's kind of on its sides, and the H is on its side. So those aren't I's, those are H's. And it shows the one electron that belongs to hydrogen. And it's sharing that electron. And since hydrogen's in the first row, it only needs 2 electrons to feel full. So it only needs to borrow 1 electron temporarily from oxygen. And both of them do that. But hydrogen only has 1 proton in its nucleus. It can't really pull this shared electron from oxygen as well as oxygen pulls its electrons in. And oxygen's very electronegative. And so the electrons tend to all spend more time around the oxygen side. So it tends to be a little bit negative. That's okay. And the hydrogens tend to be partially positive. So we have this polarized shape because water has its 2 hydrogens kind of next to each other, since its other electrons, I don't know if you see, other electrons are on the other side of the water molecule. So it creates this non-symmetrical shape. And that's important for ionic compounds, and acids and bases, which we're going to talk about later, also dissolve well. Okay, because they might contribute to hydrogen concentration. So they might have hydrogen ion, or they might have hydroxide ion. And so they're usually ionic or partially ionic compounds, or have an ionic end on them. Okay. We'll talk about more of that later. Okay. So water is a polar molecule. And because of that, we have a lot of stuff that happens in water. It's really important. And we call it, it's polar. Anything that dissolves in it is hydrophilic. Water's attracted to other hydrogen water molecules. Okay, so yeah, let's say that hydrophilic. Anything that's attracted to water, by the way, is called hydrophilic, and it has an uneven sharing of electrons. Okay, so uneven, remember, electron sharing. And it's attracted. Yeah, that's philic, means you have an affiliation to, yeah, water. You like it. The bond that holds water molecules together, um, the hydrogens and the oxygens together, is the covalent bond, right? So that's still a strong bond. So water tends to stay together for the most part. Within the body, this is a cohesiveness of water because water kind of stays with water. It helps mostly keep plasma within that's your blood, the water in your blood. It's called plasma, and it keeps it hopefully within a continuous stream in the blood vessels. It can ooze around, but it generally tends to stay with each other unless there's a high pressure or there's lots of holes or lots of opportunity for it to travel, or something that makes it want to travel. So it will also keep tissue fluid pretty continuous around your interstitial spaces, or the spaces around the cells. So we can constantly bathe the cells in water so that nutrients and oxygen and waste can get transported to and from cells. So we need the water to be able to like each other as it's spreading out, though, and at least not repel each other and run away. But within water, as you can see, these are Mickey Mouses. This is the partially positive end and the partially negative end. They like other water molecules because the partial negative end might be attracted to the partial positive end, and vice versa. Okay, so they tend to like each other. That's why they have this hydrophilic property. They're not very. This isn't very strong bond, by the way. These are very weak. They just have an affinity for it. They're like, oh, that's nice. All right, so they're weak. But important, in not just water, but other organic compounds actually have the same similar scenario where they might have a partially positive or partially negative end, and they might be attracted to the oxygen or hydrogen in water. We call it hydrogen bonds because the hydrogen is pretty positive, and it's going to be mostly what causes that happen. We can also talk about van der Waals and other intermolecular bonds, but they're also the same idea. Just atoms are just a little attracted to each other. They're not part of the compound of that molecule. Okay, so like large molecules, like proteins and DNA, they have specific functions that depend on their three-dimensional shape. Often these shapes are maintained by hydrogen bonds. Yeah, that's why the two strands of DNA stay together, and that's why you can pull them apart too. So it's not super strong in these intermolecular bonds that are between two different molecules. Okay, so that weak attraction of intermolecular bonds. That's all I'm going to say about that, but that's a whole ball of wax there, and just got to know that they're going to be holding the DNA molecules together until it's time for them to split. It's not a big deal. Chemical reactions, okay, they happen in your body. They occur when what you get at the end is chemically different than what you started, and that only happens when you break bonds or make bonds with different atoms. So the atom bonds have changed, so the properties and the chemistry of the product is different than what you reacted, than what you started with, your reactants. So, for example, a synthesis reaction is where you're just making something. You're combining things and you're making them. So A plus B, those stand for one type of element or compound, and another type of element or compound, and just stick them together. Maybe it's an ionic bond. It's usually a covalent bond, though. And we write it as a compound. Cation first, if that's a cation, and anion second, if that's an anion. For example, oxygen and magnesium got together and it was like, OMG, You can put an arrow or an equal sign. Usually it's an arrow because it usually happens in one direction. And we'll be able to make magnesium oxide, not OMG. It's always the cation first, saying that they become ions. So this is something, it's an ionic compound. We don't write the charges when they're together. They're neutralized together. All right, so 2 oxygens came into this reaction, 2 magnesiums came out, and then 2 magnesium oxide compounds, 2 magnesium oxide molecules were formed, and that's why the 2 is in front, is because the formula is MgO, but there's 2 sets of them. So synthesis, sticking things together. Decomposition would be the reverse, maybe compound AB, so they're stuck together, and they just break apart. So decomposition, if something's decomposing, it's breaking apart. For example, you could have 2 water molecules, and you could put electricity through them and actually break them apart into 2 hydrogen gas molecules. Hydrogen gas is always H2. It's always diatomic. Just like on oxygen, you can have oxygen is diatomic as well, but we only have 1 resulting from this reaction. So 2 water molecules go in and they can split, and then those oxygens form together. They're oxygen twins, and then 2 molecules of hydrogen will also be spat out. So decomposition, breaking down. Exchange reactions are where maybe they swap partners. So maybe AB reacts with CD and forms AD and CB. And if you're fancy and you remember that the cation comes first and the cation is positive and it's going to want to go with the anion of the second, you create a rainbow. The outsides go with each other and insides go with each other. That's why I put the AD together and the CB together. You don't have to remember that, but that's just how that usually happens if they're ionic compounds. For example, sodium hydroxide plus hydrochloric acid, HCl, are going to neutralize each other. You put a base and acid together, which we'll learn about later. You're going to form a salt. There's sodium chloride plus water. And yeah, that happens. And that is an acid-base reaction too, but we're going to study that later. So it's a neutralization or acid-base reaction is a fancy type of exchange reaction. A lot of reactions are fancy types of exchange reactions. Yeah, so that's what we're going to say for now. We're going to wrap it up next time, talking about more of the biochemistry of inorganic compounds, and then we're going to go into organic compounds that are prevalent in your body and the chemistry that they create there. And we're going to talk about acids, bases, and we'll talk about the other organic compounds, or we'll talk about proteins, lipids, carbohydrates, and nucleic acids. Thank you, ladies and gentlemen, for joining this. And let me know if you have any questions, and hopefully we can clear those up for you. All right. Have a great day and take care. Until next time, we'll see you later.